Today we're going to continue our discussion of limits, and what I want to do is focus on the piecewise functions and limits of them as we talk and continue to talk limits. So when we talk about a piecewise function, remember, has multiple parts to the function. And what we're going to do today is look at the graphical approach to those limits. So in order to look at the graphical approach, we obviously have to look at a graph. And then we're going to determine, do those two branches come together to a single value, to a single y value, as that x value gets closer and closer to the x values that we want. So looking at example 1, we're taking a limit as x goes to 0 of this function f of x, which is defined as a piecewise function, x squared if x is less than or equal to 0, and 2x if x is greater than 0. So the first thing I'm going to do is sketch a graph of this function. And we know that x squared, if x is less than 0, we know x squared is parabolic. We know that we're cutting it at 0, so we have this imaginary line at 0, and we normally drew in that dotted line as we started talking about graphing them in pre-calculus. If I plug in that 0, I know I get 0. I know I'm defined at x equals 0 as being x squared, so 0 squared is 0. And I know it's that parabolic function, so it looks like that. Likewise, my 2x, if x is greater than 0, I can graph that. I know, again, I'm only looking at x values larger than 0. If I plug in my 0, I would get 0 out, 2 times 0. That'd be an open circle at 0, 0. I already have a closed circle, so my function is going to be defined at 0, 0. And from there, I'm going to come up and over with a slope of 2. So there's my graph. So I have a parabolic function that goes into a linear function from left to right. So as I look at the limit as x approaches 0, so now I'm looking at my branches as x gets closer and closer to 0. And that value is going to be 0. So my limit as x approaches 0 of that function is 0, because my two branches come to that value of 0. And all I want to do today is kind of look at more examples of where we're going to see some things of piecewise functions. So in example 2, as x approaches 2, and notice this value that we're taking the limit to, and the value over here that we're restricting the pieces of, are going to relate to each other. It wouldn't necessarily make sense to take the limit as x approaches 1 if we're breaking it at 2, because we just look at that one part of it. So we'll continue here, x squared if x is less than 2. So we know, again, x squared is parabolic. There's our 2 value. We would be up here at about 4 if it were defined. In this case, it's not defined. So we come down, reaching our vertex at 0 and going back up to the left. 3x minus 2. Again, if I were to plug 2 in there, I get 6 minus 2, which is 4. 3x minus 2 is a linear function, slope of 3. So I know from that 4, I'm coming up a linear. So again, I have a quadratic that goes into a linear function. Here, the limit as x approaches 2, my branches are getting closer and closer and closer to that y value of 4. Notice the function is not defined like it was before. In our previous example, it was defined at x equals 0. When we plugged in 0, we got 0 out. In this case, it's not defined, but the limit is defined. The limit, because the two branches get closer and closer to 4, that tells us the limit is 4. In example 3, really as x is closer to negative 1, what's happening with our function? So again, we have x if x is less than negative 1. So that's a linear function when x is less than negative 1. Here's x equals negative 1. If I were to plug in negative 1 for x, I would get negative 1 out. But I can't. We're not equal to. So it's going to be an open circle there. We had a positive slope going in to negative 1. So that's that part of the graph. Here we have 3 if x equals negative 1. So that tells us that we're defined when x equals -1, we have the value of 3. That just gives us a single point for our graph. And then we have x plus 1, the absolute value, if x is greater than -1. So what that's going to do is going to be a v. Our vertex is at -1. We have a slope of 1 coming up and out of it. The other part of the v, we don't necessarily need to write or draw because it's not defined to the left of -1. So then our graph, again, that's an open circle. Since we plug in -1, we can't equal -1 in this case. So it gives us our 0. So now we're looking, well, we have the value is 3. Do the two branches, though, come together at the same point? So from the left side here, it's coming here to -1. On the right side, that branch is coming to 0 as we get closer and closer to x equals -1. So since those two branches don't come together, this limit, we say, does not exist. In our last example, we're going to give you some information and you're going to be able to sketch a graph. So in example 4, we want to sketch a graph given that f of 2 equals 3. The limit as x approaches 2 of f of x is 1. The value at -1 is 2. And the limit as x approaches -1 does not exist. So with these, there are many ways that you can draw these. You can almost say there's an infinite number of graphs that's going to take care of this, and there are, because we can draw an infinite number of functions. But ultimately, we're interested in making this information correct. So what I like to do is draw in what we have to have. We know that f of 2 has to equal 3. So when I go over to x equals 2, this function has to be 3. I also know the limit as x approaches 2 of f of x has to equal 1. So what does that mean? Remember, the limit is talking about the branches of the graph. So from the left side and to the right side, again, it doesn't matter how we come in or go out. As we get closer and closer to 2, it's got to come together at 1. Not necessarily equal to, but it has to come together. The two branches have to become together, maybe at a whole. So remember, when f of x was 2, we had a value. So the limit cannot equal the value in this case because they're not the same. So from the left side, and I'm just going to draw a small little section because we don't know what else is happening here. So we're going to draw a small little line here, and we're going to put in an open circle to show that the limit is going to equal 1. So as we get closer to 2 from the left side, we're getting closer to 1 on the y value. And when we come out, we can come out again anywhere we want as long as these two branches appear to be getting closer and closer and closer to each other. Not necessarily touching, because if they were to touch, they'd have to touch necessarily up here. All right, and then f of -1, this is going to say it's at 2. So over here at -1, we have a closed circle at -2. But then a limit as x goes to -1 doesn't exist. So what does that mean? It can mean a lot of things. So remember, the biggest thing, it means that when we get closer to -1, these two branches don't come together. So how do they not come together? Well, we don't necessarily know with this information. It could be that there's a asymptote there, or one-sided asymptote if you wish, and then maybe this comes in to a point. It could be that the graph comes in to an asymptote, and this side comes into an asymptote, but we're actually defined for the graph of that. So we really don't know what's happening, so we can kind of make up whatever we want. Maybe this side comes into the point, and then maybe from the left side, we're coming in something like that. And then there's our graph. We can connect these two pieces of the graph, and then we go on up maybe something like that. That's just one example of what that could look like. We could spend all afternoon, morning, night, We could spend the rest of the year graphing and sketching something that looks like this. So maybe we know that f of 2 was 3. So we know that value there. We know we had that open circle. So this is pretty solid there. But maybe this was just a linear function coming out like this. I'm not going to continue that just yet. And then over here at -1, again, we had that value of 2. And then the limit didn't exist. So maybe we had a nice asymptote that came down through here on this one side, and this came up as an absolute value, maybe. So that'd be another graph that would make this true, because this limit here doesn't exist, but the value does exist. One more, just because I feel the need to want to do something like that. I don't know. So again, we know this value is here. We know this open circle is here. These two branches have to come together. Maybe it comes down like this. From there, again over here, we know that this value existed, but the limit doesn't. So maybe it curves back up here. Again, we have an asymptote through there. And then maybe, just maybe, I don't know why, but maybe you had an asymptote that this went that way. So again, another graph. So a lot of different ways you can sketch these graphs as long as you have this information to be true. That's what we're looking for. Enjoy sketching those.